Our next speaker is Mr. Guy De Leonardo. In the program, you have Mr. Joe Masterangelino, who unfortunately could not attend, but we are delighted to have Guy here with us, Mr. De Leonardo, General Manager, Gas Power System Products. He is a manager for utility-scale power plants for GE Power, gas power system business. In this role, Guy leads the lifecycle strategy for advanced gas turbines, steam turbines, generators, power plants, including new products, product upgrades, to address customer, industry, and regulatory needs. He joined GE in 1991 and has over 25 years' experience in power generation industry. And prior to a current role, Guy held leadership position in GE Power and Water, GE Global Research in Schenectady, New York, developing products and technologies for steam, gas, and wind turbines, as well as gasification, healthcare, and aviation. He received his bachelor's and master's from mechanical engineering from RPI, a very good friend of mine is the dean. Nice having you with us.
So it is a pleasure to be here. And with 25 years in the industry, like Theo's comment, the last 10 years have been impressive. Change in the industry, our customers, markets. As somebody with a technical background, I never thought would see what we see in today's industry. It always used to be 60% combined cycle efficiency was the equivalent of the 4-minute mile. Now you hear us talking about 61, 62, 63, 65% efficiency. There's a lot of uncertainty in the market and the industry. I can tell you this, though. Customers want to pay less tomorrow than they do today. So everything we do and everything you do has to drive productivity in the industry. So I'm going to talk through the market outlook, business perspectives, and then technology elements across the cycle and the system that are shaping that and transforming the industry. From a needs perspective, if you look through the world, 1 in 6 people are without electricity. That's the motivating need. If we look over the next 10 years, there will be 3,000 megawatts across all generation sources added to grids globally. That'll drive a $5 trillion spend. That $5 trillion spend turns into $124 trillion across the ecosystem. So this is the motivating need. From a technology perspective, from a business perspective, how do we do that reliably, cost-effectively, and in a sustainable way? So if you look here on the left, this is how we see the next 10 years over the generating sources. For the first time, gas is the single biggest type of fuel generation in the mix at 28%. So this is over 10 years. Next, you still have a place for coal. I'm showing you here capacity. There's also an energy view. So you can think of capacity as the arteries in your body and the energy that flows through it is really what's coming from these assets. So from a generation perspective, first time gas, then coal, and without question, the growth of wind has been unprecedented, and it's been economic. And I'll talk a bit more, too, about things like solar generation as well as energy storage. It is about the economics. If we look at solar energy, for instance, especially utility scale, in the last 10 years, the cost per kilowatt is 1/7 of what it was. Energy storage, of course, continues to grow. Right now, I would tell you it's more in a frequency regulation perspective, not an intraday or an intra-week type trading in the grids that could drive dispatch from overnight to during the day. So here we have the additions. On the left, a lot of the factors shaping this. So we still see about a 2 to 3% annual growth rate in energy from gas resources. The need for diverse solutions. So not only is it about the efficiency from a capital and an OpEx perspective, how does it play with renewables? When we look at this operating flexibility, we consider start time. So can we ramp a full power plant to full load in under 30 minutes? How does it ramp? We would like to see at least a minimum of 10% of the plant's power per minute to ramp for when the sun doesn't shine or the wind doesn't blow. Other aspects like turn down, very important. I'll talk about how the technologies work to support that. In addition, we have regulatory aspects, COP21, a lot of disruption and uncertainty throughout the world, different speeds. If I look at GDP growth, especially places like China, affecting what are they doing with respect to coal, renewables, what's the growth that they see from a generation perspective, very different than in the States, certainly to Europe, to Africa, and Southeast Asia. So this is the makeup going forward from a market perspective. If I look at from a generation perspective, we really see it as three segments. Call it fast power. Can we have power in 3 months? It's typically trailer-mounted engines, somewhere on the class of 10 to 30 megawatt gas turbines. In the middle, we have anywhere from 30, we would consider that up to about a 200 megawatt class gas turbine. We call this intermediate. A lot of diverse needs here from a fuel flexibility perspective, operating flexibility perspective, combined heat and power needs, very typical here in this space. And then finally, the large utility scale power on the far right. And this is where you'll hear from mainly in the industry, we'll term it large F and large H class. You'll also hear about J class, which are the super high efficient, super large machines in this class. And if I look here, if I start from the right, this is where you'll always get the lowest cost of electricity and the lowest dollar per kilowatt installed. If I were here 10 years ago, I would have told you we're typically looking at about $1,000 per kilowatt on the right here. We're seeing that head towards $400 per kilowatt. And it's not just a matter of profitability for the OEMs. It's a matter of sustainability for the industry. So the good news is that we continue to drive down and find that productivity. The size brings that CapEx productivity. There's no question about it. If I were to look at the world again 10 years ago, largest engines were about 300 megawatts. We're up to 550, 560 megawatts in a gas turbine today. It's a 500 metric ton turbine. And it has to drive productivity in its material use across, and we take those technologies and flow them down to the left. So just a view of the different types of power plants that we look at, and here's our proof point. Earlier last year in France, this is our first combined cycle in Bouchain. It's actually a coal repower. Surprisingly enough, about the same size here at 605 megawatts, and on a net basis, set a world record for 62.22% combined cycle efficiency. So on a specific basis, 62.22% of the fuel coming out and going to electricity. In addition, the ability to start in under 30 minutes. So this is full load from command, full megawatts to the grid. You can see some of the capacity aspects. But again, through advanced materials, system integration, from the gas cycle to the steam cycle to the electrical assets around the plant, of course driving a small footprint, but this is really the state of the art. Our view is we'll continue to break this record every year. Why? Because we have to be relevant. And it's really, and how is that possible? I would tell you it's very simple. Everyone in this room would understand. Just make it run hotter. So we're pushing over 1,650 degrees of firing temperature in the gas turbines. So of course it's about cooling. It's about materials. It's the life. It's not just this CapEx productivity I talk about or fuel. It's also about the serviceability and the operating expenses that go with servicing the gas turbine and the overall power plant. We talk a lot about the benefits of how we work across GE with an aviation business, a gas business, oil and gas, as well as other corporate support. And if I walk through every aspect of that turbine, I can talk to you about the sciences and the technologies that come together, whether it's in the front of the engine, on large-scale aerodynamics, to the middle of the engine with the combustion, to maintain, certainly first, the nitrous ox emissions, of course, is your first headwind when you're pushing temperature in an engine, but there's dynamics issues. How does that work? What's the operability and the technologies that you need to be able to start the machine, accelerate the machine, and load the machine? If I talk in the back end of the machine, of course, this is where all the technologies come together of the aerodynamics, heat transfer, coatings, and cooling schemes. And then this last part, and you might find a little strange here, we talk about product cost as a technology. How does that work? Through the supply chain, through the material selection, through the manufacturing. How do we place POs in the system? How do we partner with providers through this global supply chain to deliver this at the right cost? And you're going to hear, I'm sure, a lot through the week on additive technologies, and I can assure you it's not a fad. We've worked about 15 years on the science. We have parts in commercial operation here. But as all the OEMs would state, it's truly unlocking new design spaces. The intricate features that we can put, whether it's into fuel nozzle components here that you can see on the screen, or even hot gas path components from shrouds to vanes, someday in the actual blading, we'll be able to use additive, but it's about the materials that you can print with. Cobalts, chromes, nickel superalloys. It's about lower costs. It's about putting multiple components together to be able to print those. So we have this in commercial operation in the F class on the left. On the right class, this is for the H class. And it's a bit hard to see. You're looking up at the combustion system. But what used to be a very complex component-based assembly now is completely printed. Took a lot of time to figure out those material sets, at least 150 material parameters, process parameters, on how to control the powder loading, the timing, lasers, et cetera. From a customer perspective and an operational perspective, it's simple for us. Operate at higher temperatures. Manage the nitrous oxide emissions. Less fuel, more efficiency, it's less CO2 per kilowatt hour. Other aspects that you need when you're talking about, in this case, a combustion system, things like turn down and operability. And then lastly, that service component of what a customer sees as operating and maintenance cost being their service cost has to be durable. So we expect to be able to build this, put it in the field, and not look at it for 32,000 hours. That's a big deal. Getting that type of durability and lifetime in these components, again, that are operating sufficiently over their melting temperatures. So continue to look more here for what additive will continue to do, whether it's cold parts, combustion parts, turbine parts. Will we ever print an entire hot gas path? I don't think so, but it'll continue to grow in the percentage of the components of a gas turbine engine. And I could say that, too, this from a technology perspective, the other last part of this is really industrializing this technology. If you go pull the panels back off of these machines, a lot of little pulleys and whatnot. When you talk about whether it's parts on demand or even in an industrial setting, it's going to take a lot to get the right production rates through with this kind of technology to get the quality and the durability that we have to have for the industry. I also want to talk a little bit here about the steam cycle and some of the technologies here that are driving the productivity. Typically, the first thing you look at in a steam cycle, almost like a gas turbine, is pressure and temperature levels. So where's this going from a pressure and temperature perspective? If you take today around 185 bar, 600 C would be about the limit that you'd see in combined cycle. We see these pushing to over 220 bar and over 620 C, heading towards supercritical operation. Why? It's essentially free energy from the perspective of the combined cycle power plant. So this is, of course, yielding exhaust energy to kilowatts. And the whole point of this is about the thermoeconomics of that. You raise pressure, everything gets thicker, all the way from the heat recovery steam generator, pressure parts, all the way through the piping, the valving, and the steam turbine. You push temperature, you're into new material classes, typically getting out of steels into high chromes and nickels. So first point is pushing pressure and temperature. If I look on the heat recovery steam generator, it's really about, again, the materials of construction there and the joining of dissimilar materials throughout tubes to headers and managing that cyclic life as well. So you'll keep hearing us talk about, hey, it's not just about efficiency. We need the operating flexibility. Can I daily start-stop that? What happens if you crack a tube deep in the forest to a header? The maintenance aspects and implications are not good from a customer perspective. So A lot of work getting done on the heat recovery steam side. On the steam turbine side, I would call this more traditional technology advancements in aerodynamics, sealing, and again, from this lifetime perspective, everyone still expects a 30-year lifetime out of the steam turbine. And to look at it basically on 10-year maintenance intervals. So a bit here about technologies continuing to drive, and you absolutely need this when we talk about 63, 64, 65% combined cycle efficiencies. You have to have these super 40% efficiencies out of the steam cycle in order to achieve that. This next set is really what we consider our digital thread or digital ecosystem. And this goes from the design perspective here, from a concept. Of course, this is completely computer automated, and the codes going to advanced manufacturing. And you do see the makeup here from an additive perspective of that next generation combustion system. Again, opening up design spaces, tolerances, moving into full-scale validation, and the ability to test in a quick loop, talking about 50 to 75% reduction in the cycle time it takes to go from a concept to a product. So across this entire digital thread, a lot of investments. First on the IT infrastructure to tie it together, then from the testing and the data science. Right now in the industry, this is probably one of our biggest investments alongside the technology is the full-scale validation of the complete turbine system. So it's one thing to do component design, subsystem testing, even system testing. It's really the advent of reliable, high-tech powers is understanding the interactions across those systems. So a lot of investment spent in the sensors and the testing and of course, the comparison and the feedback into the design cycle to enable that entire thread. And lastly here, I show this in a linear way. So today, I mentioned the world record earlier last year at 62.22%. So I would call that 2012 technology level. Today, on the same basis, we're somewhere at in the mid-63s here, clearly heading and see a path to 65% from traditional technologies, of course, like aerodynamics, heat transfer, material systems, combustion capability, and in the steam cycle. We see this convergence, of course, of the digital world, software, the advent of software-defined machines, again, from design to build and to fleet management. This independent energy diversity, how does this play with renewables, solar, wind, energy storage? It's both distributed and centralized. Of course, centralized is the traditional large-scale utility. We also see the advent, whether it's rural electrification, small CHP needs, powering universities, hospitals throughout the world, of a need for solutions in the distributed space. And then there's the disruptors. I pick on one here called the active generator. This is the whole ability to take a non-synchronous machine like a 50 hertz gas turbine and put it into a 60 hertz grid. Why? Because as the scaling rules would have it, the 50 hertz gas turbine is typically 44% bigger than the 60 hertz gas turbine. So if I could take the same engine and run it in 60 hertz, I just found 44% more output, and that drives the productivity. Single engine across the world, we get an NPI, a new product introduction, and an investment productivity in that as well. This is something we've demoed up to 350 megawatts here last year, and we'll continue to push that. But it's those types of disruptors. You'll see in the program elements of pulse detonation combustion. That's good for another 2 points on here, by the way. So in some forums globally, you'll hear about the path to 67%. I can tell you, if you even asked me 5 years ago, I would have said no way. I would have said the economics would never have supported 65%. So it's marketing. And then I've personally participated in the product and the technology development and witnessed 62 and 63% type operation. So it will come, and it will come through technology. There's no question about it. So that all has to do with the continuous innovation. So truly, through technology, transforming the industry and really redefining the art of what's possible. So I thank you for your time. I wish you a great week here of learning and contribution, and appreciate the opportunity to speak here this morning. Thank you. Thank you.